Hi, everybody. Welcome to chapter 27. This chapter is going to be kind of applicable to some of the stuff we've talked about in prior chapters. So we'll see some cardiovascular system, respiratory system, digestive system issues come in as we focus on how our body regulates our fluid balance, our electrolyte balance, and our acid-base balance. And some of those are intermixed, some of them are standalone. So we'll just kind of go ahead and start working through all these different aspects of maintaining homeostasis. The first thing I wanted to kind of lay out are the fluid compartments, because we're going to talk about fluid balance first. So we have our two major fluid compartments. They are the ICF and the ECF. And this stands for intercellular fluid and extracellular fluid. So when we take a look at where fluid, mainly water, is in our cells, it can be in any of these two compartments. Now, the ICF is really only in one place. It is your cytosol, right? Basically, it is the cytoplasm within all of your cells. So ICF is the volume of fluid that is inside of your cells. ECF is everything else, all of the fluid that's outside of your body cells. And there's lots of different places where ECF can be found. So the most common one that people are pretty familiar with is your blood plasma. So we saw this back in our cardiovascular system. Blood plasma is 90-something% water, so most of our fluids are going to be found in the plasma. We also should be familiar with lymph, with our lymphatic system. So we know lymph is fluid that's found outside of cells. And then we have interstitial fluid. Interstitial fluid. So those are kind of the three biggies of where we're going to find extracellular fluid. So blood plasma, lymph fluid, and interstitial fluid. And all of those are really intermingling, because interstitial fluid is created by the filtration of blood plasma at the capillary beds, and lymph is made by the collection of that interstitial fluid into the lymphatic vessels. So blood plasma, lymph, and interstitial fluid are always kind of mixing and interacting with each other at those capillary beds. But if you remember, we have lots of other fluids that are outside of cells that would belong in this ECF compartment that might be smaller volumes. So if you remember, we had the humors in our eyes, right? Vitreous humor and aqueous humor. We had our lymphs in our ears, peri and endolymphs. Let's see, what other kind of fluids do we have outside of cells beyond plasma, lymph, and interstitial fluid? We had synovial fluid. I think that might be it. There might be another one I'm missing. And serous fluids. So like your pericardial fluid, your peritoneal fluid, your pleural fluid. Yeah. I think these are what we call our minor compartments. So what we're really pretty much going to be focusing on in the ECF is our blood plasma and our interstitial fluid, and ICF is cytosol. That's the only place it can be. All right, so also before we move on to the next slide, taking a look at the fluid shifts and fluid balances, I wanted to talk about some key things. These are listed here in the notes, these basic concepts of regulating fluid and electrolyte balance. So the first one is when we monitor homeostasis, when we are trying to figure out what's going on, maybe osmotic concentration or electrolyte concentration, all we can ever do is monitor ECF. There is no way that we can put receptors, chemoreceptors, baroreceptors, stretch receptors inside of a cell. So anytime we're monitoring homeostasis, we're monitoring blood plasma or lymph or interstitial fluid or the humors, or, oh, I forgot one. Ooh, this one's really important. CSF, oh my gosh, can't forget CSF, because we have lots of chemoreceptors in our brain that's monitoring what's going on in the CSF. So when we talk about homeostasis, is it the ECF that's in homeostasis? But that's okay to not monitor the ICF, because there is constant communication between the ECF and the ICF. They're only difference, or only their barrier, is a plasma membrane, a phospholipid bilayer. And we know that things are going to be moving across that phospholipid bilayer either by simple diffusion, facilitated diffusion, or active transport. So you're going to have a lot of communication between the ICF and the ECF. So if you're monitoring the ECF, that's an indirect indication of what's going on with the ICF. So that was our first basic concept. The second one is we don't have receptors that directly monitor electrolyte levels. So we do not have receptors that can say, oh, we have 5 molar sodium concentration or anything like that. We measure our 5 molar actual 5,000 sodium ions. We measure the osmolarity, or we measure the ratio of solute to water concentration. So it's more of the ratio of the solutes in the solvent that our chemoreceptors pick up on, not a direct measurement of the actual ion levels. That was number 2. Number 3, our cells cannot actively transport water. So water moves via osmosis. We can actively transport ions and solutes, which then water will follow that solute, but we can't pump water. Water has to move passively via osmosis. That was number 3. And number 4 is kind of relational. So in the notes it says our body's content of water or electrolytes will rise if dietary gains rise, and will fall if we losses exceed gains. So it's kind of common sense. Our levels will go up if we have more, and they will go down if we lose more. So that's kind of common sense. All right, so in the notes, as I'm going through the notes here for chapter 27, there's a little blurb on all the hormones. I'm not going to spend too much time on those because we've seen them quite a few times already, but you can review ADH, aldosterone, and natriuretic peptides. These are key hormones in regulating your fluid and electrolyte balances, maintaining your blood pressure, blood volume, sodium and potassium levels, and those types of things. Okay, so just some factoids, if you will, about the composition of our body and our different fluid compartments. So the bar graphs on the top are showing you the distribution of our solid components. This is actual matter, organic molecules. So if we break it down in kilograms, most of our body is composed of proteins, and then lipids, and then minerals like calcium and phosphorus, carbohydrates, and then miscellaneous, kind of like a potpourri mix. So we have, if we're to, let's see, take a 150-pound person, about 70 pounds is going to be solid components, about 85 pounds are going to be liquid components. And if we take a look, the water is going to be found in liters. They're showing you liters here of ICF compared to your ECF. And again, those 2 major volumes or compartments in the ECF is going to be plasma, interstitial fluid, and the other is kind of all those other things we just listed on the prior slide. Then in the bar graph, they're kind of taking those measurements in the bar graph and turning them into these pie charts between a male and female. So for males and females, the ratio is a little bit different between fluid and solid. So males have a little bit more water percentage, about 60-40 split, and women are a little bit more close to a 50-50 split between the ECF, the ICF, and your solid components. If we take a look at electrolytes, so things that we're going to be following in these compartments, the ICF versus the ECF. So these 2 things together are major compartments of the ECF, plasma and interstitial fluid, ICF over here. So inside of cells of our cations, our positively charged ions, we should be comfortable that we have a whole bunch of potassium on the inside of cells. We really learned that back in muscle physiology. And on the outside of cells, we have a whole bunch of the negatively charged ions. Or sorry, this is still inside of cells. Our negatively charged ions are primarily going to be phosphates and proteins. And that's going to, if we remember, that also allowed us to have that negatively charged inner part of the membrane compared to the outside. If we take a look at the interstitial fluid and blood plasma, they're pretty similar. We'll notice that sodium is the major cation, the major positive ion outside of cells, which we saw before. And chlorine being the major anion, with a a significant amount of bicarb in the blood plasma and interstitial fluid. And that we learned back in our respiratory system, our digestive system, and our kidneys. You have a lot of bicarb. That's part of our buffer in our body systems. All right, so that's just comparing your cations and anions between your inside of your cells and your outside of your cells. Now, when we take a look at fluid gains and losses, again, a lot of this can be seen as common sense. If you kind of just follow where things are and where they go, you're going to be able to see these relationships. So water gains, well, just say water. They say fluid, but it's, water. So water gains are going to come from what we eat. Right? So I'll get the highlighter. Got a cattail coming. There. Move along, kitty. So she just came in from outside, silly girl. So absorption across the epithelium, digestive epithelium, this is coming in from our food and drink, okay? We gain a little bit from the metabolic production of water via the mitochondria. So in cellular respiration, if you remember, glucose and oxygen is converted to carbon dioxide and water and energy. So that's that water. So between what we take in from what we consume and what our cells make, we're looking at about 2.5 liters of fluid gain. And then if we have equilibrium, we should see our losses are going to be about the same. And sensible perspiration is variable. So if you're not sweating very much, you're not going to lose as much water that way. But if you are sweating a lot, you'll lose more water, which means you're going to have to balance that out with taking in more water via across the digestive epithelium. So just know that if we are out of balance between what we lose and what we gain, we would be in dehydration. If we gain more than we lose, then we'd be in hyperhydration or overhydration. So you can have imbalances on either sides of an equilibrium, kind of a homeostasis for your body. Now, when we do fluid shifts, fluid does shift. Like I said earlier, osmosis will move water from one compartment to the next following that concentration gradient. So if you remember, water follows, I'm going to be a little bit more general because a lot of times this phrase says water follows salt, but it doesn't always have to be salt. It could be sugar, it could be proteins, it could be other electrolytes. So water follows solute. So wherever the higher concentration of solute is, the hypertonic environment, compared to a hypotonic environment, water will go from the hypo to the hyper. So let's say in this first scenario, your ICF and your ECF are balanced. They're isotonic, right? So you guys got to remember these terms from general bio. So isotonic. We have the same amount of solute on either side. The blue compartment is acting as the ECF. So this could be blood plasma. So let's say you are losing volume in your ECF, but you're holding on to electrolytes. So you're not losing any solute, but you're losing water. So now comparing between your ICF and your ECF, this is now hyper and this is now hypo. So now you have a concentration gradient. You have a difference between the fluid inside your cells and the fluid outside of your cells. So this fluid shift is going to drive this higher water concentration to the lower water concentration or the higher solutes. Water follows salt. And what will happen is the isotonicity will be reached again. That's our equilibrium right here. But the net result is both ECF and ICF will be lower in overall volume and a higher concentration ratio because we're keeping the same amount of solutes, we just have less water to dissolve them in. But at least now they're at equilibrium, so we can be back to isotonicity and not shifting fluids in any other direction. We could do the same thing if we wanted to kind of go in the opposite direction. So let's say we have we are isotonic here, and instead of the ECF becoming hypertonic, let's make the ECF hypotonic. So this might be a consumption of a whole lot of water. So drinking a whole lot of fresh water, or kidney problems where your kidneys cannot diffuse or release excess water. So now if our cells are the hypertonic environment, water will move this way, kind of increasing both of the volumes will be going up, and eventually the water will move in to try to create an equilibrium. The problem with this, though, is we have just plasma membranes as a barrier to our cells. If too much water, if this concentration of water of our blood being hypotonic to our hypertonic cells, if this influx of water is too significant, the cells will swell up. You could have lots of swelling, your neurons will swell, your brain will swell, your tissues will swell, and eventually they could burst, right? And then your cells die, and you could die. So our body has ways to compensate, but sometimes if you overhydrate, if you drink too much pure water, your kidneys cannot keep pace. And in that case, people have died by overhydration. Either drugs can trigger consuming too much water or blocking your kidneys from functioning, or there was that story, it's kind of semi-famous now, of a contest for people to win a Wii video game system way back when those were popular. There was Hold Your Wii, W-E-E for a Wii, W-I-I. It was a radio contest. People were asked to drink in a short period of time to see who could last the longest without having to go to the bathroom. And one of the contestants died. It was a woman. People were calling in, nurses were calling in and saying, this isn't safe, you can't do this. But the radio hosts were like, it's just water, that's not a bad thing. But it is a bad thing, is because you took your body out of homeostasis so far that it cannot compensate. The kidneys can only do so much. And we'll see that when we get to the compensation a little bit later. All right, so I think that is the talk about fluid balance. So fluid balance is pretty straightforward. Take in what you pee out or poop out. You lose a little bit of water during your feces. And if you can keep those two things in balance, then you will be in balance. If you're off by a little bit, so if you're sweating and exercising, you might be in a little bit of a dehydration state, but usually your body has ways to fix that, right? So ADH, aldosterone. If you have too much water, you can use your natriuretic peptides. But if you go too extreme in either one of those directions, then you could really be in trouble. All right, so I will be back with some electrolyte balance. See you next time.